Good evening, all the participants. We are going to start this FDP in a short while. We are waiting for participants to join in so that maximum can get the benefit of our inaugural session. So please have patience. We are about to start the FDP in few minutes. Thank you. Good evening. Good evening, all the participants. Respected Vice Principal, HOD Madam, distinguished speakers, esteemed faculty members, and dear participants. On behalf of Marathwada Mitra Mandas College of Engineering, Pune, I am pleased to extend a warm and heartfelt welcome to the inaugural session of this exciting 6-day online FDP on Practical Insights into RF System Design, which is sponsored by AICTE ATAL Academy and organized by the Department of ENTC Engineering MMCOE Pune. I kindly request all participants to keep their microphones muted during the session. If you have any questions, feel free to submit them in the comment box and they will be addressed after the inaugural session. This program is a reflection of our dedication to fostering academic excellence and innovation. We are truly honored to have distinguished speakers and participants joining us from across the country. To start today's session on an uplifting note, let us invoke the blessings of Goddess of Knowledge. Please join me in welcoming our student Ishani Kulkarni, who will now present the Saraswati Vandana. Over to you, Ishani. You can start the Vandana.
Thank you, ma'am. या कुन्देन्द्रतुषारहारधवला या शुभ्रवस्त्रामृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिर्देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती शुक्लां ब्रह्मविचारसारपरमा आद्या जगद्व्यापिनीं वीणापुस्तकधारिणीम् अभयदां जाढ्यान्धकारापहाम् हस्ते स्फटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरी भगवती बुद्धिप्रदां शारदाम्.
Thank you, Ishani, for that beautiful and soulful rendition. Now I formally request our HOD and the coordinator, Dr. A.S. Bhatlavande, to share more about this remarkable initiative. Over to you, HOD ma'am.
Thank you, Sampada madam. Good evening, esteemed dignitaries, respected faculty members, industry experts, college higher authorities, and dear participants. I, Dr. Anjali Bhatlavande, welcome you all to the inauguration of AICT ATAL sponsored 6-day online faculty development program on practical insights into RF system design. I extend my gratitude to All India Council for Technical Education, ATAL Academy, for granting us the opportunity to organize this FDP. Marathwada Mitra Mandas College of Engineering is grateful for this support. The vision of our institute is in line with AICT's emphasis on promoting research and innovation. I assure AICT on behalf of all the participants that we will make the most of this opportunity. So in coming 6 days, FDP focuses on mainly 4 domains. Firstly, RF components and applications, then RF design, RFIC design, then topics like PLL, power amplifiers, passive components, and safety analysis, and lastly, textile antenna for RFID. So we have renowned experts in these domains. So these resource persons are from United States, Italy, renowned industries and academia. So we have these experts like Dr. Chinmay Mahabar, then Mr. Abhay Kulkarni, Dr. Ashok Khedkar, Dr. Nijamuri, Dr. R.P. Panwar, Dr. Rajesh Singh, Dr. Amit Khade, Dr. Andrew Mitchell, Dr. Vivek Ratnaparkhi, and Dr. Anurag Nigam. So these are the resource persons who are experts in their domains. Our participants, now we will come to the participants. Our participants come from various backgrounds, bringing great experience and curiosity. We have participants from various states like Bengal, Orissa, then Chhattisgarh, Karnataka, Tamil Nadu, etc. So I urge everyone to actively participate, ask questions, and contribute to this workshop to make this event a grand success. So, if in a case of any query or support, kindly contact our organizing team. We have many platforms like you can send email, you can send message, or we have WhatsApp group. So those who have not joined WhatsApp group, you can join the WhatsApp group. We will send link in chat box. Before I conclude, I would like to express my sincere appreciation to our organizing team, resource persons, and our principal sir and honorable management. So, once again, I am thankful to our participant, resource persons, and honorable management. So, make this event successful, grand success, and warm welcome to this workshop again. So, thank you, Sampada madam. You can continue.
Thank you, Dr. Bhatlavande, for giving us a comprehensive overview of the FDP and its significance. Now, without wasting any time, we will proceed to the closing of this inaugural session. I invite Mrs. Harshada Burande to deliver the vote of thanks.
Thank you, ma'am. Good evening, everyone. It's an honor to deliver a vote of thanks on the occasion of the inaugural session of Practical Insights into RF System Design. First, I extend my sincere gratitude to the management of Marathwada Mitra Mandal for their support in organizing this FDP and fostering academic growth at MMCOE. A special thanks to our principal, Dr. B. N. Gohakar, for his guidance and leadership in the making this event possible, as well as to our vice principals, Dr. K. R. Patil, Ms. Swati Deshmukh, for their invaluable contributions. I also thank our dedicated coordinator, Dr. A. S. Bhatlavande, and the organizing team, faculty, and supporting staff for ensuring the smooth conduction of this program. Finally, my heartfelt appreciation to all the participants whose enthusiasm will make the initiative successful. I am confident that this FDP will be a platform for meaningful discussions and knowledge exchange. Thank you, and I wish everyone an exciting and enriching experience ahead. Thank you.
Thank you, Burande ma'am. So, before we end this session, allow me to remind you of the session schedule for today, which is day 1 of the FDP. We have 2 sessions scheduled for today. The first session will be held from 6:30 to 8 p.m. and that will be followed by the second session from 8 p.m. to 9:30 p.m. So here we end the inaugural session, and again, as I said, without wasting any time, we will proceed to our day's first session, which is session number 1. So today's expert is Dr. Chinmay Mahabar. Let me give you his introduction. Dr. Chinmay Mahabar is an active researcher in wireless communications, focusing on autonomous vehicles. He completed his bachelor's degree from MMCOE Pune. Yes, I am feeling proud that he is our alumnus. He received his MS and PhD degree from the University of Massachusetts, Dartmouth, and since he has been researching at Toyota's Infotech Research and Development Labs in Mountain View, California. He is actively working on the evaluation of 4G LTE, 5G NR vehicle communication systems for the automotive industry. And he is also working on standardizations of the 3GPP group. Dr. Mahabar has publications in IEEE. He was an associate editor for the IEEE Internet of Things Journal and has a strong background in teaching and academic collaborations in India, US, Germany, and Italy. He's passionate about mentoring the next generation of engineers and scientists through his work in robotics and STEM education. Outside of the work, Chinmay enjoys playing the piano and exploring the world of music. So, this was the introduction for our today's speaker. So, the topic which he will be discussed is Introduction to RF Components and the Parameters. Let me tell you something about today's topic. The fascinating world of radio frequencies stretching way back in time and all the way into the future. We are going to explore the components, parameters, the history, and where this technology might take us next. But it's not just about theory. We will see how academic research and real world industry work hand in hand to make it all happen. And of course, we are going to uncover some things science still hasn't quite solved. So get ready to be curious because we are about to dive into the past, present, and future of RF technology. With that short introduction, I give mic to Dr. Mahabar. Over to you, Dr. Mahabar.
Yes, thank you so much, Tausim, and a very good evening to all of you. And I wish you all a very happy new year. Um, Let me share my screen. Uh, Please let me know if my screen is visible and if I'm audible right now.
Yes, sir. Your screen is perfectly visible and you are
Yeah.
perfectly audible.
Okay. Yeah. So thank you so much, Tausim ma'am, for the warm words, and also thank you so much, HOD ma'am, all the faculty members, and all the expertise in that area. It's really an honor to be a part of this talk and share some of my experiences into this world of RF. I know we all have expertise in our quite niche areas during doing the research. So what I'll try to do is maybe give a brief introduction, and I'm sure some of the concepts would be already familiar to you. But I'll try to join how the concepts are related to the existing ongoing research. Maybe that would spark some new conversation. So, of course, I would be very glad to hear your thoughts on this as well. So, while before starting any topic, this Rumsfeld matrix is quite an useful tool which I have been using. So, if you can see on the screen, there are like four quadrants classified basically based upon what we know and the things we know. So, in the quadrant of known knowns would be the things which we know and what we know. So, for instance, we might be aware of we can ride the bicycle, and we know that we can ride the bicycle. So, those things come under the known knowns. Then there are few things which are known unknowns, so that we know what we don't know. For example, maybe solving a Rubik's cube. We are aware that we don't know about these concepts. Then there are unknown knowns. Maybe we don't realize we know that. So maybe while texting on the phone or while typing on the keyboard, we don't know the exact positions, but yet we can type by without looking at it. So we are just not realized about it. And the final things are the unknown unknowns. So we don't even know what we don't know in this kind of field. So this is like one of the biggest mysteries. Maybe, for instance, it could be a source of energy which could be invented after 50 years. Now, the reason I'm explaining this matrix is we are aware of certain concepts, and these fall into few of these quadrants. So, to get a better understanding, the goal of any research or maybe this seminar would be to shift most of the topics from all of these three quadrants into the known knowns so that we are more aware of it. But at the same time, we can also see another arrow which goes from known knowns to known unknowns. So when we start looking into certain topics, we realize, oh, I was aware of these concepts, but maybe it leads to some of the unsolved research areas. So, for instance, we know how to ride a bicycle, we are aware of it, but we might not know how to program a robot to do that. So then that becomes the known unknown. So I'll try to what do we say, refer to the RF topics from this quadrant. So that was an example from day-to-day life. But if we start going towards the technical side, some of the known knowns could be the basic formula of C is equal to F lambda. So we know about this formula. Then the things we don't know, maybe the recent research which is going on in the beam forming or the MIMO systems. We are aware of those concepts, but we might not be aware of the small technical nitty-gritties in those areas. So if we know that and if you are interested, then slowly those topics can come into the known knowns. Or unknown knowns could be, suppose if you have to select a Wi-Fi plan for either our university, college, or at home, and if we know how many users are there, we can select, okay, this much bandwidth, this much data rate could be sufficient for my usage. But we might not know the exact mathematical formulas for it. We might just have an intuition. So that could be the unknown knowns. So while going through these seminars, we can discover some of these topics over here and then try to make sure we slowly drift towards the known knowns. Now, while introducing to any topic, these days getting answers is very easy. We can just type it into the Google or we can just type it into the ChatGPT and we can get a very detailed explanations of most of the things. So getting answer is not a challenge these days, but finding a good research question is very important. I think a good research question is like an engine to a car; it drives itself. So I might not be qualified to give all the answers, but definitely through these discussions we can come up with very good research questions, and then based upon our interests and uh, what do we say, technical insights and research expertise, we can start going in that direction. So at least if I help to uncover some of the questions on this topic, I think that would be a good aim for this. Now, as was mentioned in the introduction, I am a researcher at Toyota Infotech Labs, and I basically work in the vehicular communication. But throughout my education, I did work on the Bluetooth protocol in terms of robotics. During my undergrad, I worked on the IR-based NEC protocol, the ZigBee, the Wi-Fi. These are the recent ones. So most of the talks would be driven to the 4G, 5G standardizations and of course the upcoming 6G. Then we try to solve some of the challenges related to the vehicular communication. Like one of the biggest challenges, both of them are in continuous motion. So how RF domain is getting impacted by these recent challenges. So I still consider myself as a student of wireless communication, and I'm still trying to learn many new things about it. These are some of my publications which I've been working on. Uh, now, when we say RF, it's basically a part of the electromagnetic spectrum. So, when we look at the electromagnetic spectrum, basically this is the visible part. So, we see from the purple to the infrared areas. But beyond that, as the wavelength starts increasing or the frequency starts reducing, we get the IR, then microwaves, radar, and here lies the radio or the radio frequency, which is of interest. And as we go towards the shorter wavelength, which is the ultraviolet or gamma rays or cosmic rays, uh, these would be the topics of interest. But uh, usually, when we say RF, it's basically the whole electromagnetic spectrum. So, this is quite fascinating because we can't see these waves, but yet they are so much part of our day to day life, right? From this video call which we are having or any communication which we are having right now. Uh, on the left hand corner, you can see an electron. So, if you look at the size, even a small electron moving generates an EM wave right up till the cosmic waves which are generated by the sun. So, if the we say the wavelength over here is around like 400 nanometers and it exceeds very too small amount to the atomic values of this electron, and the longest wavelength for these cosmic waves, the wavelength could be as long as the diameter of the earth. So in literal sense, this is a very wide spectrum, and As we can see, each specific slice or frequency of the spectrum has its own properties, which we try to use in practical applications or theoretical applications. So that's a very brief idea of how we are approaching this. So when we are diving into this world of RF, research has always been going on over the past 200 years or 250 years or so. And right now, we have this distinction of specific academic research or a technical research. But this field always goes, or any field, the research always goes hand in hand. We start with the academia, then those things get commercialized, and then again, to improve the efficiency of the commercial products, the research goes back to academia. So that's why I have tried to maybe create this two columns, but that's just for our understanding. But at the very core value, both of these researches are quite same. That's what I have realized. Then again, there are two concepts. One is phenomena, and other are the laws. Like we can see the sun rising in the east. That's a phenomena. But to understand more about it, when we discovered the gravitational laws and everything, we came up with an explanation for that. So uh, the Faraday first discovered this phenomena that okay, when we move the magnetic pole around here, the electricity is generated, but the laws weren't invented. But it also happens that sometimes laws are discovered first, and then we uncover the phenomena, which was done by Maxwell. Like Maxwell laws were discovered in 1860, but those weren't proved. So that's where the actual RF propagation or electromagnetism started. Maybe it's like 200 years ago. But if you're aware of the news which came around a month ago, which was like November 26, 2024, Voyager 1, which was launched, they had shut it down because to save the energy, and it was rebooted again. So when that communication happened, this satellite was around like 25 billion kilometers away. So the range of the communication of the research has increased from like say few millimeters till billions of kilometers. So we can see with what pace this field is progressing right now, and that's why it creates a many lot of challenges. So it's very exciting to look at all of these approaches of the RF domain. Now, this is, I'm sure we all are aware of the basic Maxwell theorems, and these are four of them. So, when we see electromagnetic, it's just a relation between the electric waves and the magnetic waves. So, the E means the electric, so it's based upon the charge, and B is the magnetic. Uh, and the last two equations just show an interrelation between them, like the change in magnetic causes an electric field, and vice versa, change in electric causes magnetic. But the reason I included this is even though the laws were invented 200 years ago, a research about them is still going on. For example, if you look at this second equation of magnetic theorem, it says that like the divergence or the sum of all the vectors is always zero. That means the north and south pole can't exist independently out of each other. Uh, there, if we consider any magnet, it always has a north and south pole, and that's why it nullifies each other, and we get a sum of zero. But still, the research is going on the magnetic monopole. So, can either just a north pole or south pole exist? So, the reason I'm trying to introduce this is because even though such fundamental laws have been discovered, the research about it doesn't stop. This is just a small video to elaborate on that. This was funded in 2012, and this scientist has received many awards about it.
Okay, so in nature, when you have magnets that you're familiar with as children, and so they have a north and a south
Can someone please confirm if the audio of the video is still like? Can you hear the video?
pole, just like the Earth itself has a north pole and a south
Thank you so
pole.
much.
And so it behaves like a little stick with a north pole stuck at the end and the south pole is the other end. Now, when you try and separate these, the problem with magnets is when you split them, you end up with another south pole and another north pole. So each part that you split, you end up as being a north and south and a north and south. So you can't allow this north pole and the south pole to become free to act independently. What a magnetic monopole is if you imagine that somehow you're able to free, to liberate the north and south pole at the end of your bar magnet, then that is a magnetic monopole. It will create magnetic.
Okay, this is a very long video, but maybe you can take a look at it later. So if that is still going on, then why do we need these magnet like monopoles or so on? So research about super insulators,
the hiding place of magnetic monopoles.
and
The concept of single electrical charge is ubiquitous in physics. Whether they're protons, electrons, or quarks, particles carrying electrical charges are fundamental to our universe.
so insulators are definitely useful in all the electronics and so on. So the reason I mentioned this is the research about even the basic concepts is still going on. So it doesn't mean that if this is fundamental, we stop going through it and so on. So this is also quite exciting thing which I find about the RF world. So we discussed about the Maxwell and so on, which was like 250 years ago. After that, the experiments conducted by Hertz were able to finally prove practically that EM waves exist or RF wave exist. The reason I'm mentioning this is when we look at the practical insights, if we just keep ourselves restricted to the current time, we aren't able to understand the challenges or complexities of it. So this practical insight gives another approach on how this experimentations can be helped to verify the laws. So that's also another topic. If we are interested in the RF, you can go in this direction as well. Uh, so we all know frequencies measured in hertz. It's based upon this great scientist Henrik Hertz. So what the experiment basically did was we create a spark over here. If there's a change in voltage, the EM wave is generated, and if a spark is generated over here and the EM wave travels through the space over here, then another spark should be created over here. So this experiment was done like 250 years ago, which first time uh, a transmission of EM wave or the RF wave was uncovered, and then this whole field started. Uh, so looking at this video would be quite exciting. I'll just try to show.
Without a radio set, though, it's not easy to detect these waves, and most scientists didn't believe they existed till just over 100 years ago. What finally convinced them was an experiment performed by the physicist Heinrich Hertz in 1887. It was first demonstrated in... This was Hertz's receiver. It's simply a loop of copper wire. Well, the big spark creates radio waves with enough energy to make a tiny spark jump across the gap between these balls in the receiver. Well, if you look carefully, you can just see the spark jumping across the gap.
So that was the experiment over here. Sometimes when we are so much engrossed in the theory, we sometimes forget the beauty of these research which was going on like over 100 years ago and which led to this discovery. So it's always quite refreshing to look back and see over there. I should not forget to mention Jesse Bose, who was also quite actively working over here, Jagdish Chandra Bose, and he also greatly contributed to the microwave communication of this. And once we started with this transmission of EM waves, slowly it started going towards the technical or tech side or the industry side. So radios were invented, and Marconi was one of the first industrial expert in this, or the father of radio. So when we start transmitting the waves or the RF waves, there became a need of modulation. So a wave has like three basic components: amplitude, wavelength, and frequency. I'll just go fast over it because it's quite basic concepts. But basically, we need modulation to transmit over a longer range. Since it's more immune to noise, we improve the quality of reception. Multiplexing, that means if there are many users, many transmitters, there's no interference among them. Also, we adjust the bandwidth. So there are different kinds of modulation basically dealing with these three parameters: amplitude, wave, frequency, and phase of the wave. So initially, first an amplitude modulation was invented. Basically, even if we just create a small spark using a battery, we can see its impact on a nearby radio. So a change in voltage is transmitted through the space, and a receptor can detect it. So that was the first kind of modulation which was being discovered, used, but again it's immune to a lot of kind of noise, which is atmospheric noise, or it can't go through the obstacles and so on. So that's where the FM modulation started, and in India, All India Radio was established in 1936. Just to get a brief idea, this was like the first radio transmission which took place in US. It was like in 1920, which is like 100 years ago.
This is KDKA of the Westinghouse Electric and Manufacturing Company in East Pittsburgh, Pennsylvania. We shall now broadcast the election returns.
Yeah, so what you heard right now was the first radio broadcast transmission which took place over here. And in the video, I'm not playing it because of the lack of time, but in the video he mentioned that whoever hears this transmission can please get back to us because we aren't aware how far it is going. So that was quite interesting to watch. Then after that, AIM. So when this radio transmission in AIM started, they realized that okay, it's not going to a lot of users. So then FM transmission was used, and this was one of the first all India broadcasts which took place. And is Ramanujan Singh. He was basically one of the broadcast in charge in All India Radio, and he gave a continuous 7-hour radio broadcast transmission when the event of Mahatma Gandhi took place. So this research is not only related to the tech field, but it what do we say? It unknowingly influences the economic side, the social side, the entertainment side. So this is a very broad topic, and that's why I wanted to include this image over here, because sometimes we are looking at the research from such a narrow perspective, we forget what it's impacting. So that was an image. Then lastly, this is the phase modulation which we are still using in the recent Wi-Fi transmission as well, when we mention about QPSK and so on. So this is the current one, which is a bit complex one because the circuitry of this phase modulation equipment is quite complex. This is just an evolution of transmitters. So whenever we consider a component of RF transmission, we just have a transmitter, an antenna to transmit it, and a receiver. These could be the basic building blocks. So it started with this size, and right now we are over here. So this was a chip which was researched by Qualcomm. It has an mmWave antenna, it has a transmitter, it has a modem inside it, and it's still at the size of a fingernail. So this just shows that the research is going in both the hardware side of the components as well as the actual transmission. Now, once we started going towards the digital modulation and we started using digital signals, we were able to cater the need of the commercialization. So it increased the robustness, capacity, the reach, because right now we are also working on the satellite communications. So the range has definitely increased, and also the quality of communication. This is another concept which is multiplexing. So right now we mentioned about how the spark or the EM wave was sent from one transmitter to one receiver. But what happens when there are multiple transmitters and multiple receivers going through just one channel? So how should we differentiate between them? So of course the first one which was invented was the FDMA, or it's basically a frequency division multiple access. So we can see the division is made up on the frequency. So suppose there are 4 transmitters and receivers, then we can see each one uses its own frequency channel. Suppose the 100 kilohertz, then 120 kilohertz, 140 kilohertz, and so on. And it avoids the interference, and many users are being able to connect. But we see that it requires a lot of bandwidth. So gradually the research went to TDMA, where it is divided upon the time. So you can take it the analogy of the way we watch movies. We have different frames, but since those are moving at a very high speed, we are able to see the motion in the movies. So similarly, just a single part of the data is transmitted at a given time instant, and then that takes on continuously. So that's a TDMA, and then gradually we went to CDMA, which is code division. So it has both time as well as frequency. This is just a mathematical explanation of how the CDMA takes place. I will not go into the details of it, but it is quite, at that time it was quite novel to look at it, because every user, suppose we are looking at 3 different users, every user has one specific code. That code is used in the operation of all the 3 different users. Then it is added over here. We have a single transmission channel. Then once that single code is transmitted over here, and if we are aware of the main code of this user, we can again decode the original value. So just by using a single code, it takes place over here. So that was the time of CDMA, which was used in, I guess, 2G or 2G, I guess, in 2G. So these are just some of the concepts which we looked till now. We started with the laws, then analog and digital modulations, broadcasting, communication. But that was a part of broadcast. So when there was just a single transmitter, it was trying to connect to all the users. But then the challenge started happening when we started coming to the mobile communication or digital based communication. So there were multiple transmitters and multiple receivers using the same channel. So that was another interesting research challenge over here. So this is another basic